Comparison of axial compressive load capacity of piles by different methods. Abstract: determining the correct bearing capacity of piles has important technical and economic significance for the construction using the pile foundation. However, this is a complicated problem because the bearing capacity of piles depends on many different factors such as soil conditions, geometrical dimensions of piles, method of pile construction, etc. Pile load static compression test in the field is usually performed to verify and estimate the bearing capacity. Due to time and some other practical conditions, some constructions cannot load on piles until failure. In this article, test data is analyzed to predict the ultimate load of pre-stressed concrete spun pile PHC. This analysis is based on the results of the 4 static compression test, which was carried out at Riverside Apartment construction site in Ho Chi Minh City. 4 piles have a diameter of 600 mm and a length of about 38 ma 41 m. The geological survey at the site was conducted to a maximum depth of 80 m. The ultimate bearing capacity of piles is determined by different methods including Vietnamese standard TCVN 10304:2014, 2014, Formula of Japanese Institute of Architects, 1988, Graph method of Chin-Kondner, 1970, Decourt, 1999, Mazurkiewicz, 2003. Based on the value of ultimate load capacity of 4 piles were calculated by 5 different methods, it is shown that each method can estimate different ultimate load capacity of piles. Within the scope of this study, the number of 4 test piles, and 5 methods of calculating pile load capacity selected, it shows that when using the formula Institute of Architecture of Japan AAIJ, 1988, calculates the ultimate bearing capacity of piles giving more reliable results than the other 4 methods. Compared with the obtained value when the static compression failing test TP1, the TCVN and the Mazurkiewicz method give the results that are not much different from each other. Keywords: pile capacity, pile load test, ultimate bearing capacity. Introduction. Pile foundation is commonly used in high-rise building because of its load capacity. Pile foundation is used when the ground has the soft soil layer on the surface, which is not able to bear the construction load. In this case, piles transfer load to the deeper hard soil layer. Prediction and determination: pile bearing capacity have a great influence on the economic technical factors of the construction. Using highly reliable method in calculating the bearing capacity makes the selection of pile bearing capacity, pile cross-section, pile length quickly, accurately, and cost-effectively. The correlation between the pile head displacement caused by the axial compressive load, which is shown in the graph of pile's static compression test, is one of the bases of determining the ultimate compressive load capacity for the design pile foundation. Due to some limited conditions, in practice, it is usually to choose the maximum compressive load acting on the pile head about 1,5 to 2 times the design load in the test at the site. Therefore, in some cases, the pile static compressive test has not given the ultimate bearing capacity of piles. Mazurkiewicz, Chin-Kondner, and Decourt have proposed graphical methods based on the correlation between compressive load and pile displacement to predict the ultimate bearing capacity of piles. The research content of this paper is the synthesis of static compression test data of 4 piles of high-rise apartment built in Ho Chi Minh City, accompanied by data of the pressure force when constructing piles into the ground, such as analyzing the load displacement curve of piles, calculating the ultimate compressive capacity of piles by a number of different methods, and building the correlations between the ultimate compressive capacity of piles and piling stopping force, maximum. Pile test load and pile design bearing capacity. From the analysis and comparison, the conclusions of the research can be drawn. Literature review. There have been many studies on predicting the bearing capacity of piles from theoretical and experimental results. These are the works of Mirza, 1997, 1, D. Waker and Pahlavi 2, Nabil 3, Brinch Hansen 4, Mazurkiewicz 5. Mirza, 1997, 1 introduced a simple method for calculating the frictional resistance of driven piles into clay. This method is based on the correlation between the characteristic indicators and strength of soils derived from marine clay. The results show that except for the short piles in the hard to very hard clay, the predictions are agreement with the measure results at the site. This correlation is presented that the skin friction component can be calculated and the importance of liquidity index in calculating static capacity is shown. De Waker and Pahlavi, 2002 analyzed the load test data at the site to predict the ultimate bearing capacity of piles. This analysis was based on 40 results of pile load test obtained from various civil and infrastructure projects constructed in the Mumbai region of India. This study showed that the collected data were analyzed by different methods such as semi-empirical and graphical methods. Nabil 3 studied the group effect of board piles based on the field test performed at a site in South Surah, Kuwait. The study also includes load testing on single piles in compression and tension states. There are 2 groups of piles made, each group consists of 5 piles. The spacing of piles in the selected pile group is 2 and 3 times the pile diameter. The group coefficient value found is 1.22 and 1.93 in case the distance between the 2 piles is 2d and 3d respectively, where d is the board pile diameter. In a number of documents and different standards, the results of pile compression test have been explained and been proposed to determine the ultimate load capacity from this test. J. Brinch-Hansen 4 proposed an estimate for calculating the ultimate bearing capacity. Chu method of Brinch-Hansen 80% have the following simple relation. Straight line. Mazurkiewicz proposed a method of extrapolating load and settlement curves 5-6. Accordingly, the proposed method is, the plot of the loading test curve toward the settlement was based on the result of load test in the observed location. Drawing lines from so selected settlement points until they cross the curve. Vertical line is being drawn until it reaches loading pivot. From the cross of the load, a line with an angle of 450 is being made until it crosses the next line. These points are connected until straight line is formed. The cross of the straight line with loading pivot is its ultimate load. This method gives the assumption that loading curve movement forms the shape of parabola. Therefore, the value of the collapsing loads, obtained by using Mazurkiewicz method, should approach 80% of the standardized criteria. Another method that can determine the ultimate bearing capacity of piles proposed by Chin, based on the research results of Chin-Kondner 7, allows the extrapolation of the failure load in the static load tests. The method consists of dividing each respective load applied by the settlements and put it in the y-axis. In turn, the x-axis places the settlements obtained during the static load test. The load limit is given by the inverse of the slope formed by the points plotted on the graph. Another chart method is proposed by Decourt, which method is similar to those used in the method of Chin-Kondner 7 and Hansen 8. To apply this method, divide each load with its corresponding settlement and plot the resulting value against the applied load. The Decourt extrapolation load limit is the value of load at the intercept and the slope of the line as given in the equation below. Construction site is as shown in Figure 1. The soil profile at the site is reported to consist of clay and sand, and is presented in Figure 2. The water table varies from 3.3 m to 5.0 m below the ground surface. Test pile parameters. Pile selected in this study is pre-stressed concrete spun pile PHC with D equals 600 mm with the design load capacity QD equals 250 ton, the working load. Fig 6. Pre-stressed concrete spun pile PHC at the site. At the site, 4 test piles labeled as TP1, TP2, TP3, and TP4 respectively are compressed into the ground to the design depth and ensure not to exceed the maximum pile pressure value max. Method of compressing the pile by using the load from the counterweight to create the force to push the pile to the ground. Correlation between pile pressing force, FP, and depth of embedment Z for each pile are shown in Figure 7. Fig 7. Relationship between pile pressure value and pile tip depth. With each pile we have found that pile pressing force tends to increases proportionally to the pile tip depth and reaches the maximum value of Fp max equals 503.2 tons when the pile is stopped. Determine pile capacity. The objective of research was to calculate the amount of bearing capacity of single pile, based on several conventional methods. It is obtained based on soil investigation in the field. They were value of SPT, liquidity index, boring log, data for one location from some points of observation and the analysis of the bearing capacity of the single pile and its settlement, based on loading test data. In the research scope of this paper, it is calculating the ultimate bearing capacity of the piles by using the formula based on Vietnamese standards, Pile Foundation Design Standard, TCVN 10304, 2014, 12 and from the pile test results. Prediction of pile load capacity using Vietnamese code. First, based on the geological cross-section in Figure 2 and the location of the pile, establish the actual geological column that the experimental pile is placed in. The stratigraphic column and the thickness of each soil layer that the 4 piles in the survey placed in are shown on the Figures 8 and the Figures 9. The pile diameter is taken as 600 mm and the lengths of experimental piles TP1, TP2, TP3, and TP4 are 37.9 m, 38.6 m, 41.8 m and 41.8 m, respectively. Then, the formulas for determining the ultimate bearing capacity of piles in Vietnamese standards are applied to calculate the pile bearing capacity. The ultimate bearing capacity of piles according to the standard uses the symbol RCU. The parameters in this formula strictly comply with the provisions of the standard. Its value depends on the geometrical characteristics of the pile, the physical and mechanical parameters of the soil obtained from laboratory experiments such as liquidity index, physical state, soil type, and tip depth. Case 2, based on the formula Standard Institute of Architecture of Japan AAIJ, 1988, A also shown in the appendix of Vietnamese Standard TCVN 10304:2014, Section G 3.2. Compressive loading and unloading are shown in Figures 11, 12, 13, and 14 respectively. The value of pile head displacement corresponding to each level of compressive load with the maximum at each stage of the piles is summarized in Table 4. The ultimate load capacity of 4 piles are shown on the figures from Figure 5 to Figure 7 when calculated by 5 different methods. Let the symbol Qmax be the maximum load of the static compression test at the site and Q is the estimate of the ultimate load capacity of the pile by different methods. Calculate the ratio between Q and Qmax and those values are compared between test piles as well as between different calculation methods. The results are presented in Figure 35 and Figure 36. Set the symbol QD to be the working load of the pile. Calculate the ratio between Q and QD and those values are compared between test piles as well as between different calculation methods. The results are presented in Figure 37 and Figure 38. Some of the comments made are as follows. With one pile, different calculation methods result in the ultimate bearing capacity of piles having different values. The method of calculation by the formula has greater results than the method based on the graph of the load relationship and the pile settlement in the pile static compression test. The pile load capacity calculated according to the AIJ formula gives the maximum value. With 4 static compression test piles in the field, TP1 pile has reached the failure value, which means that the value of the ultimate load capacity of this pile has been determined as Q equals 500 tons. Therefore, it can be seen that the calculation method according to TCVN and AIJ formulas as well as Mazurkiewicz's graphical method gives relatively consistent results compared to the other 2 methods. For piles TP2, TP3, and TP4, the pile compression test at the site reached the value of Qmax equals 550 tons, however, these piles have not reached the pile failure limit. Therefore, it can be commented that the calculation of the bearing capacity according to the formula of the Japanese Institute of Architects AAIJ, 1988, is relatively more reliable than the other 4 methods. It is difficult to comment on which calculation method gives more reliable results. With this pile condition, it is found that this method gives more reliable results, but this method gives unreliable results compared to other pile conditions. The results of calculating the ultimate bearing capacity of each pile are different, depending on each geological form as well as on the value of compressive load and pile displacement when testing piles statically and using different calculation methods. If we compare the working load of the pile with the ultimate load capacity calculated by 5 different methods. Conclusions. The ultimate capacity CHU for each test pile was predicted using 5 methods stated above, including 2 methods using theory formula and 3 graphical methods based on static load test that are used in the evaluation of the pile load test. It is difficult to comment on which calculation method gives more reliable results. With this pile condition, it is found that this method gives more reliable results, but this method gives unreliable results compared to other pile conditions. The results of calculating the ultimate bearing capacity of each pile are different, depending on each geological form as well as on the value of compressive load and pile displacement when testing piles statically and using different calculation methods. Each method can estimate different ultimate load capacity of piles. Within the scope of this study, the number of 4 test piles, and 5 methods of calculating pile load capacity selected, it shows that when using the formula Institute of Architecture of Japan AAIJ, 1988, calculates the ultimate bearing capacity of piles, giving more reliable results than the other 4 methods. Compared with the obtained value when the static compression failing test TP1, the TCVN and the Mazurkiewicz method give the results that are not much different from each other. Acknowledgement. The authors would like to acknowledge the Kotukins Construction Joint Stock Company and ICP International Construction Project and Consultancy JSC for their valuable assistance.